Hello everyone, Dr. Chen here. In this video, we are going to learn electric potential, and we're going to start with electric potential energy, and then we define electric potential based on electric potential energy, and show some example in calculation of electric potential energy and electric potential. So let's first recall what we learned about gravitational potential energy. Now, first of all, the reason we can define a gravitational potential energy is that gravity is a conservative force. What that means is that if you have an object starting from position A, end up at position B, the work done by gravity does not depend on the path this object takes from A to B, so it can take any path, just two different paths in the plot, and any other path. So as long as it starts from point A, end up at point B, the work done by gravity is always mgh, force times displacement times cosine the angle between displacement and force, if it's a constant force, right? Okay, so let's recall the change of potential energy is defined as the negative of the work done by the conservative force from initial position to final position. So you can also, of course, write it as the work done by this conservative force from A to B equals to the negative of changed potential energy. And for us, for gravitational force, it's a work done is always mgh1 subtract mgh2, so you can define this one as is initial potential energy, this one as is final potential energy. Now we're ready to introduce what is electric potential energy. Now, first of course, electric force is a conservative force, and we can prove that using the work done by a point charge on another point charge. Now, if you have more than one point charge, what you need to do is just need to calculate the work done individually. So what shows here, which is not required for you, but is a rigorous proof that as long as you have 2-point charge, the work done on this charge moving from one location to another is independent of the path it took. It really only depends on the initial position and the final position. So this is why electric force is a conservative force, and this is why the reason why we can define electric potential energy. Now we can compare to the gravitational potential energy case that you have a ball dropping. Now we create a uniform electric field. Now it looks very similar to gravitational field now. So the electric field is pointing down, and the magnitude is everywhere the same. And if you put a positive charge moving from position A to B, the work done by this electric force is independent of the path it took. And we can calculate what's the work done by this electric force, right? Now, because the work done by electric force is independent of the path it took, we'll take this path, which is the easiest one to calculate. The force is a constant, which is Q times E, Q0 times E, that's the force, times the magnitude of the displacement, which is D, times the angle between electric field and the displacement, and you can see that in the same direction, so the angle between them is 0. The work done is Q0 ED. So in this case, positive charge moving from positive end of the electric field to the negative end in this situation. The work done by the electric force is positive and is given by Q0ED. Now, if we can recall, energy conservation is potential energy decreased and the potential energy will transfer to kinetic energy. The total energy, potential energy plus kinetic energy is still going to be a constant, and this is energy conservation. So the difference between electric potential energy and the gravitational potential energy is that you have two different kind of charges. Now if you have a positive charge move inside the electric field, so if your charge, positive charge move in the same direction of the electric field, then the potential energy is going to be decreased. If you so this direction of V give us potential energy decrease. Now if you have a velocity which is in the opposite direction of electric field, your potential energy is going to be increased. Now if you have a negative charge, it's going to be different. If you have a negative charge, you have an electric field pointing down, the force is going to be pointing up. The electric force on this negative charge. So if this charge is moving in this direction, the electric potential energy is going to be decreasing. Now if you have negative charge moving in the direction of the electric field, you have potential energy increase. So that's the difference between electric potential energy and gravitational potential energy. In gravitational potential energy, your mass is always positive. But for charge, you can have positive charge or negative charge. We can calculate what would be the work done by so you have a point charge Q here, you have a test charge particle Q0 moving from the position A to position B along this radial direction. You can use Coulomb's law. So we start from Coulomb's law. What will be the work done by the electric force? So we need to do an integration of electric force, and the electric force is Coulomb's law, goes as 1 over r squared. So basically, what you need to do is do an integration of r squared, and we kind of know what kind of what do we have, right? Sorry, it's the integration of 1 over r squared, so actually is r to the negative power of 2. And if you do the integration, you find is actually 1 over r negative. And then you put the integral limit, you'll find the work done by the electric force is given by this one. So we can call the first term, which is K Q0 over RA, is electric potential energy of Q0 at A, and this is the electric potential energy for Q0 at position B. Now remember, the change of electric potential energy is defined as negative of work done by this conservative force. So in this case, if Q is positive, Q0 is negative, the electric potential energy is decreasing, because this conservative force is doing positive work. So change of potential energy is negative. So starting from Coulomb's law, we have calculated what would be the electric potential energy between two point charge, and is given by this equation. Of course, you can also write it as K Q0 over R, because K equals 1 over 4 pi epsilon 0. And we can define the 0 for this potential energy is that when those two charges are infinite far away from each other. And this one you can directly carry the sum of the charge into this equation. So if I have two positive charge, the potential energy between them is positive times positive give you positive. You have two negative charges, the electric potential energy is negative charge times negative charge, also give you positive energy. So the potential energy between two same sign charge is positive. Now on the other hand, if you have one positive, one negative, you're going to have negative potential energy. Now think, why is that? So when you put those two charges infinite far away from each other, potential is 0, right? So if both of them positive, what kind of force is between them? Repulsive or attractive? Now from the first lecture we know is repulsive, right? Repulsive, so when you bring them together, the force between those two charges are doing negative work. And when the force is doing negative work, the change of potential energy is positive, so you got a positive potential energy. You can do the same thing analysis for negative and a negative, right? So the force is doing negative work, potential energy increases when you bring two negative charge from infinite far away to distance r. Now on the other hand, you start with a positive and a negative charge, which is infinite far away from each other, and you bring them together. What's the force between them? Of course, it is attractive, right? And when it's attractive, when you bring them together to distance r from infinity far away, the electric force is doing positive work. So when the force is doing positive work, because your change of potential energy is negative work done by electric force, when you're doing positive work, potential energy decreases. This is why if you have a positive charge, negative charge, you're going to have a negative potential. Positive, negative give you a negative potential energy. And this is for 2-point charges. So what's going to happen if you have more than 2-point charges, for example 3 or 4? So what we can do is that we can find out all the 2x2 pairs. For example, in this one you have 4 charges, Q1, Q2, Q3, Q4, and the total electric potential energy is going to be just as the potential energy between each pair of the charges. And if you have 4 charges, you can count you have 6 pairs. 1, 2, 1, 3, 2, 3, 1, 4, 2, 4, and 3, 4. So you calculate each of those electric potential energy pairwise using the equation we have, K, Q1, Q2 over R, and then add every pair potential energy of each pair together, you find the total electric potential energy. So now let's do one example to help us understand. So it says I have 3 charges. Every charge is 1.2 microcoulomb. and they are placed at corners of equilateral triangle, and each side is 0.4 meter. I want to calculate what's the potential energy of the system. So let me label them. Let's call this one Q1, this one Q2, Q3. So from what we just discussed, the total electric potential energy should equals to U12 plus U13, U23. Three charges, we have three pairs, right? Now Q1 equals Q2 equals Q3, and distance between Q1, Q2, Q1, Q3, Q2, Q3. So let's call it R12, R13, R23 is all equal. So we have U12 equals U13 equals U23 from U of 2-point charge is K, Q1, Q2 over R12. So they all equal, well, just equal, let's see, U12. So it also, the total potential energy also equals 3 times U12. So it seems we just need to calculate what is the potential energy between Q1 and Q2 and then multiply by a factor of 3, then we find our answer. So let's calculate what is U12, K, Q1, Q2 over R12. K is 9 times 9, 10 to the power 9. So I use SI unit everywhere, so I don't need to worry about the unit. This is Q1, Q2. The distance between Q1 and Q2, which is 0.4 meter. So if I use SI unit for each number, it should just give me joules. And if I put everything into my calculator, I find this is electric potential energy between Q1 and Q2. And then as we discussed, total electric potential energy equals 3 times U12 equals 0.0971 joules. Okay, now hopefully we already understand what is electric potential energy and how to calculate it. Now we're ready to define what is electric potential. So now we have learned what is electric potential energy and how to calculate it. Now we move on to define and learn what is electric potential based on electric potential energy. So let's say we have some charge here, and they create an electric field at location A, B, and C. What I know is that if I put a charge which is Q, 10 nanocoulomb, if I put it here, I see the electric potential energy is 0. And I need to do 4 joules of work to move the charge from A to B. And I need to do 6 microjoules of work to move the charge Q from A to C. So of course, my UA is 0, so my UB, electric potential energy at B, is 4 microcoulomb. Electric potential energy at C is 6 microjoules. And this is for charge Q equals 10 nanocoulomb. So let's think what would be the work I need to do if the charge is 5 microcoulomb. if the charge is 5 microcoulomb, the force, the electric force from A to B would be halved, right? So if it's 5, I only need to do 2 microjoules of work to move the charge from A to B. Now if you double the charge to 20 nanocoulomb, the force is going to double. So I need to double the work to move charge from A to B. So if you put all the numbers together, what do we have? We have the electric potential energy at B divided by the charge of the particle I move from A to B is a constant. It's always 400 J to B. So it seems between A to B, there is a constant, and this constant is created by the distribution of charge here, even though we don't know what's the position of each individual charge. So, and this quantity, that electric potential energy, we can also call this to be change of electric potential energy from A to B, right? Divided by charge Q is potential between point A and point B. So we define electric potential like this. Because my electric potential energy at A is 0 joule divided by any charge, let's say 0 volt. So I have an electric potential at position A, and then if I have 10 nanocoulomb of charge, I move it from A to B, I need to do 4 microjoules of work, and I have 4 microjoules divided by 10 nanocoulomb give me 400 joules per coulomb. So whatever the charge I move from A to B, the electric potential energy divided by the charge is always giving me 400 joules per coulomb. So I define this 400 joules per coulomb to be the potential at position B. Now the same thing, for 10 nanocoulomb, I need 6 microjoule to move to C, so the potential at C is 600 joule per coulomb. And we call 1 joule per coulomb equals 1 volt. And this is electric potential. We say we have a charge here, either created a potential of 0 volt at position A, and a potential of 400 volt at position B, and 600 volt at the position C. You see, potential is a property at this location now. So, and each location can have its own potential. Now, it's very similar to electric field, right? But there is difference. For electric field, at each location, you will have a electric field at this location, and the electric field is a vector. Electric potential is a scalar, so at one location you can only have one potential, and it's a scalar. If you have more than one particle creating electric potential at the same location, you need to add the potential created by each individual charge up. And because the electric potential is defined from electric potential energy, electric potential is defined as electric potential energy over the charge. So the electric potential created by charge Q2 at this location is given by electric potential energy between them Q1, Q2 over R12 divided by Q1, right? And this is U12, this is U12, so it's K Q2 over R. And this is exactly the electric potential created by a point charge at a location R away from the charge. So this is a very important equation for this chapter. If you have a point charge Q at a distance r from the charge, the potential it creates is kq over r. Now, on the other hand, if you already know what is the electric potential at the location, and if you depart charge q there, then the electric potential is simply q times v at the location. So let's use one example to help us understand electric potential. You have 2-point charge. Q1 is 2.4 nanocoulomb. Q2 is negative 6.5 nanocoulomb. They are 1 meter apart, and you have position A is middle point between Q1 and Q2. Then you have point B is 0.08 meter from Q1. Point B is 0.06 meter from Q2. Now we want to find what's the potential at position A, what's the potential at B, and then in the end I want to find if you have another charge. Let's call it Q. If you have another charge which is 2.5 nanocoulomb, move from B to A, what's the work done by the electric force from Q1 and Q2? Let's solve them one by one. Let's first solve the first question. What is potential at position A? What is potential at V? So V at A would be equals to the V created by Q1 at A and the V created by Q2 at A. V created by Q1 at A is K Q1 RA1, which is the distance from A to Q1. K Q2 RA2, which is the distance from A to Q2. K Q1 RA1, Q2 RA2. 9 times 10 to the 9, and Q1 is 2.4 10 to the negative 9, and the distance between A and Q1 is 0.05 meter. Q2 is negative 6.5 10 to the negative 9. Distance from A to Q2, 0.05 volt. So pay attention, I need to keep this negative sign when you calculate electric potential. And I put all the numbers into my calculator. I find it's negative 737 volts. Now I just need to do the same thing for VB. Is K Q1 R1 B1 Q2 B2, and then my Q1 is 2.4 10 to the negative 9 coulomb. My Q2 is negative 6.5 to negative 9 coulomb. This is RB1 0.08 meter, RB2 0.06 meter. So plug in all the numbers, I find is negative 704 volts.